Hello everyone. Now we will continue with the discrete systems. In fact, the basis of any numerical method or like finite difference, finite volume and finite element depends on the discrete system. And generally we use some software packages in order to solve our engineering problems. For finite elements, it can be ANSYS, it can be Abacus, Nastran, FemLab, Altair, or there are several different commercial software packages, and also there are in-house developed softwares for finite element simulations. But more or less, all the softwares have similar structures and based on similar approach in modeling a problem. So let's see what are those steps. So first step is the preprocessing. So basically we have a geometry, okay, and what we do is we divide this geometry into sub-geometries and we call these domains. So we have a domain which is for example our object. If you are designing making an analysis of nut, it is the nut, or if it is the wrench, it's the wrench. I don't know, it may be the shaft or so on. And then you divide it into sub domains. Okay, we call each domain element. So we have finite number of elements. So this is why this method is called finite elements. Okay, so this is our first step. This is called preprocessing in all software packages. The next step is the element formulation. So of course we need a mathematical model in order to simulate our engineering problem. Then we use element formulation and develop set of equations for our problem. And what we do is we develop the formulation or write the equations for each element first. This is the first step. Okay, so next is the assembly. So what we do is, okay, we develop the equations for each element, but we are interested in the overall behavior of the system. As a result, we assemble the system of equations depending on the physical and mathematical rules. So that is the next step. After obtaining the entire system of equations, what we do is we solve the system of equations by using numerical methods. Okay, and the last step is the post-processing. Now we solve our problem, we find the deformations. So I'm just talking about a hypothetical case, in fact. So basically this means that we predict the displacements. In fact, next step is to calculate the strains from displacements. And once you calculate the strains by using the constitutive relations, you can calculate the stresses and visualize the overall behavior. Okay, so this is what we do in general for any type of modeling in numerical modeling approaches. It can be finite volume, as I said, finite difference, or others. Of course, we have elements, and we have locations in the elements which we have the unknown values of the displacements, and it may be different. You can put these points anywhere inside the element, but generally we put it on the at corners. So next we need to say computer that how the displacement varies inside the element. Therefore, we need to make an approximation of the variation of the displacement, and in fact we know from the numerical methods we use polynomials in general, or functions for the interpolations, right? So then we say that, okay, within the element, the function that I'm interested in, the property that I'm interested in, varies with this function. And by using these functions, with the use of this combination of these functions, we find how the displacement varies. Of course, we know that the strain is the derivative of the displacement, roughly speaking. Then we take the derivative of it and we calculate the strain, and from there we calculate the stresses. This is what we do in a discrete system. So basically, first step is to obtain the discrete system of our engineering problem. Of course, we have seen the discrete systems before. So remember, from statics and strength, we have truss systems, right? So we design large truss systems for the roofs, for the bridges, or for other things, for construction purposes, for load carrying purposes, and others. We have the chassis of an automotive, for example, automobile. So we have truss elements. They can be rectangular cross section. They can have a rectangular cross section. They can have circular cross section. It can be elliptic. It can be an I-beam, U-beam, or there are different types. So it doesn't matter. So remember what the truss system is. Truss system only carries force along its direction. And when we want to analyze this truss system, we use one of the methods that we use is the node-based approach. So remember that we write the force equilibrium at each node, and we combine the forces at that node, combine the forces coming from the truss elements, and we write the force equilibrium at each node. Then we develop a complete system of equations, set of equations, and then we solve it. And because our objective is whether a truss element will fail or not. What is the simplest failure criteria for us? Of course, we look at the stress. Remember that stress is the measure of the force and is defined as the force acting on it divided by the area. That's okay. If this value exceeds a certain value, we can say that, okay, that element will fail, because we want to design a system which will not fail, which will do its function. Fine. And also we know that truss element, there is no forces acting between two nodes in a truss element, right? So truss element carries load only along its direction, and certainly even though we assume that the deformations are small, there is a certain amount of deformation, so there is displacement, and there are forces acting on it. Now let's look at a simple truss element, because this is the first discrete system that we solve in our in mechanical engineering. Okay, so we have one node, we have the second node here. So this is the left one is the first node that I have on the truss element, on a truss element, let's say, and the second one, the one on the right is the second node. This is just a number that I gave in order to differ them. I can give different numbers or different, I can assign different letters also to these nodes. But since we are going to use computers, it is better to assign some numbers to each member of our design. So we have a force acting on each node. Here the superscript E denotes the element. So this is my element, truss element. I have the force acting on node 1, and I have the displacement of U is the displacement here, F is the force. I have the displacement of node 1. Similarly, I have the force acting on node 2, which is F2, and U2 is the displacement of node 2 for one dimension. Of course, many of my problems are not one-dimensional. I mean, even though there is no two-dimensional problem, sometimes I can say that my problem is two-dimensional. In such a case, I have two force components at each node and two displacement components. And certainly my member truss element has a direction in this case. Therefore, now I have two force components at each node and two displacements at each node. Therefore, I have 8 variables related to a truss element in 2 dimensions. For 1 dimension, it is just 4. Of course, for 3-dimensional problems, it increases. Certainly, I have, since force and displacement are vectoral quantities, I have 6 variables for each node, which makes totally on an element I have 12 variables. Okay, I'm an engineer. I want to design a discrete system, truss system, and I want to solve it. Now, we know that for a static equilibrium, sum of the forces acting on an element has to be 0. So this is what I see here. Okay. So as a result, forces acting on node 1 and forces acting on node 2 has to equilibrate each other. That's okay. Next thing, remember that from strength course, I assume that my material is elastic and obeys Hooke's law. So what is elastic and what's Hooke's law? So let me remind you. Remember that if you apply a force on an object, it deforms in real. When you remove the force, if it returns back to its original shape, then that material is called elastic. It can be linear elastic, it can be non-linear elastic. Okay. Now, the point is, we have different materials. For example, generally for small deformations, steel behaves as a linear elastic material, but rubber is generally a non-linear elastic material. Both are elastic. So you can think like this. You have a latex hand glove, you scratch it, and you leave it, it returns back to its original shape. So that's what the elasticity is. Okay, what's Hooke's law? Hooke's law tells me that if the relation between the stress and strain is linear, then we say that that is that's the Hooke's law. And for many problems we can say that our material obeys the Hooke's law, in fact. Okay, now remember that we have forces and displacements, so we don't have stresses and strains in our formulation, in our equilibrium equation. Now what we do is we write the stress. Stress is equal to force divided by the area, and the strain is change in displacement divided by the initial length. L is here the initial length of the truss element, and delta is the displacement. Okay. So basically, when you apply a force to a truss element which has initially a length of L, it makes a displacement. Each node makes a displacement. So the first node makes a displacement of U1e, and the second node makes a displacement of U2e, and it goes to its new position, right? Then the truss element will have a new length, L new. Now let's write the forces for each node. F2 is equal to the normal force. Here it is area multiplied by the stress, and from the Hooke's law we know that it is area multiplied by, here E is the Young modulus multiplied by the strain, and the strain is equal to delta divided by L. Now delta, the amount of elongation, is the difference between the displacements, right? Simple. It is U2e minus U1e. And the force at point 2 then can be written as K multiplied by change in length. Look, elongation. This formula is the formula is similar to the relation between force and displacement in a spring, right? And therefore here we call the small k as stiffness. It is similar to the stiffness of a spring, which means that a truss element acts like a spring, behaves like a spring. And if we put all the expressions into their places, we can see the value of the k, the stiffness of the truss element. Basically, k is equal to area multiplied by the Young modulus divided by the initial length. So now we have the expression. Which relates the forces to the displacements. So this expression tells me that force at node 2 depends on the displacement of node 1 and node 2. If I write the forces identically, I can write the force 1, force acting at node 1 on node 1 similarly. So F1 is equal to minus F2, has to be equal to minus F2, because there has to be a force equilibrium, and it is the stiffness of the truss element multiplied by U1 minus U2. Now, for computational purposes, it is better to write this set of equations or expressions in matrix vector notation. So I write the forces as column vectors, as you see here, and then I write the displacements as column vectors. Here D is the column vector of the displacement, F, which is written in bold letter, is the column vector of the force, and then I have the stiffness matrix. Here capital K is the stiffness matrix, the elemental stiffness matrix. Certainly it has elements of stiffness of the truss element, Ke, minus Ke, minus Ke, and Ke. As you see, the element stiffness matrix is symmetric because of the force equilibrium and the relation between the displacements and forces. Okay, so as a result, I can simply write the force displacement relation, here the D is the displacement vector, as seen in this expression. So it is force is equal to force acting on the nodes is equal to stiffness matrix K of the element multiplied by the displacement vector of the element. Here the superscript E denotes the elemental values. If we write the expression for the stiffness of the truss element into its place, we obtain this expression: area multiplied by the Young modulus divided by the initial length of the truss element, because it is commonly assumed that the area of the truss is constant along its length. Okay, so this is for a single truss element, but generally we have more than one truss members. For example, you may have a system as seen in this figure. As you see, we have forces acting at each acting on the system at different points. Certainly the area may change. As you see here, the cross-sectional area is smaller and the cross-sectional area is bigger on the right hand side. Also the materials may be different. So one part might be copper and the other part might be steel or brass or concrete, so whatever it is. Then what we do is we divide the system into elements depending on their properties. Generally we divide in such a manner that each element has constant properties. You can divide it in a different way, but then this will create some problems in modeling. So when I look at this problem, I see that this region has a constant area, and moreover I have a force, point load, acting here, acting on this point. Now what I do is I say that this is one of my elements and this is the other element that I have in my system, and I give a number to them. I say that this is my first element. Look at this figure. And I say that the region with a larger area is my second element. Then I put the nodes. Okay. So this is my choice, be careful. So you can give the numbers to the nodes however you like, but generally it is better if you give the numbers in a systematic way in order to simplify the operations. Okay, so I say that the one on the right side, where I have the boundary, the node that I have on the right side is 1. The middle node is 2, and the left node is 3. So if I look at the problem, element 1 has the nodes 3 and 2, and element 2 has the nodes 2 and 1. Now these numbers are called global numbers because this is my complete this is the model of my complete problem. Okay, now let me write the forces and displacements at these nodes. Now on the right hand side, my system is anchored to the wall, it's fixed, which basically means that I have I know the displacement for this node, for the node 1. So I put an overbar for the known values, and indeed I have the reaction force here. R1 is the reaction force coming from the wall. I just choose the direction as I did in statics and strength of materials, and I put all the forces from left to right. If the direction of the force is in a different direction, certainly the value that I will find will be negative. Okay, now when I come to the second node, I have a force component F2. This is an external force. I know the value of the F2, or maybe I know the displacement, but generally F2 is given. And I have the nodal displacements U2 for this node. I have the similarly, more or less it's actually it's the same for the node 3. So for node 3 I have F3 and U3. Okay, now let's look at the problem in an element wise manner. Now this is my first element. If I look at this my first element, now from the formulation, the one on the left is my first node on this node. So be careful. The nodal values for the element wise nodal values and the global the node numbers in an element wise manner and the global manner are different. So the one on the left hand side is node 1 in an element wise manner, but this is node 3 in the global system. So this is the first node of element 1, and this is the second node of element 1, and in the global system this is node 2. So let's do it like this. This is node 2 in the global system. Okay, and just a moment, sorry, and this is node 3 in the global system, but actually this is node 1 for the element. So this means that this node and this node is identical, the same node. So I basically focus on each subunit independently. Now I'm modeling my problem and I go from top to the bottom. Okay, so this is again node 2 and this is my node 1 in the global system, but actually this is node 2 in the element. So this is the node 2 of an element of the element 2, but it is the first node of my global problem. Okay. Now let's continue to analyze this system. So let me write the forces and force equilibrium for each element. Now if I look at the node 1, I have force 1 acting on node 1 and force 2 acting at node 2. Okay, so this vector F bar is the force vector of element 1. You see this, it has superscript in parentheses 1. Now let me write the forces acting on the element 2. Again, it is F2 and F1. So remember how I numbered the nodes in the global system. So node in the first node in the global system is my second node in the element system of element 2. Identically, the first node of my element 2 is the second node in the global system, and it is the same for the element 2. So the second node of my element is the second node in my global system. So this is why F21 is second member of this vector, and first node is the third node of the global system. So it is like this. This goes to this. This goes to this. This goes to this. And this goes to this. So as you see, second node of first element and first node of second element actually is the same node in the global system. Okay, then I write the force equilibrium, and I know that the sum of the forces, because these capital F's are the internal forces. Okay, now this is my pre-processing step in modeling. Now I'm discretizing the problem in order to form the elemental equations. Now I have forces acting on each element. Certainly some of the forces has to be equal to 0. So some of the internal forces has to be equilibrated by the external forces, right? This is what it means. Fine. So what we do is we sum up the internal forces of the elements, and this has to be equilibrated by the external forces. Now we have the reaction force R1 coming from the wall. We have the external forces acting on node 2, F2, and we have the external force F3 acting on node 3. There's then another thing that we do. Now remember that We know F2 and F3. These are external forces and are given to us. But we don't know the reaction force. As well, we don't know the nodal values of the internal forces. As a result, we divide this force vector into two vectors. The ones with the known values and the ones with the unknown values. R. So the ones with the known values are denoted with small f in bold, and the ones with the unknown values are denoted by small r here. Okay, now we have the system of equations, right? F and R, sum of the forces. And we have the force vectors for each element. Now we know that, for example, for node 1, we can write the relationship between the forces and displacements as seen in this expression. So F is equal to, F1 is equal to K1 multiplied by U3 minus U2. These are the global node numbers, U3 and U2. So because my first element has nodes 3 and node 2. Okay. Now I can write this equation like this. I just put an additional row, right? It will not change anything. So I have a vector with 3 components because I know that this is the second node in the global system and this is the yes. So this is the third node in the global system and this is the second node in the global system. So I can write it like this. I just change the places of the equations because if I do this matrix vector multiplication, I will obtain the relationship between the force and the displacement, and I write it like this. Okay. Now I have the force coming from the second node. The force in the second node is equal to stiffness multiplied by the difference of the displacement between the second node and the third node in the global system. It is similar for the third node. Now look, I have a vector with 3 members. I have a 3 by 3 matrix. This is elemental stiffness matrix again, which is written in global numbering, according to the global numbering. Then I have the nodal displacements U1, U2 and U3. Again, remember that these are the global node numbers. So as a result, I can write the force displacement relationship as seen in this expression. So force is equal to, force in element 1 is equal to, forces in element 1 is equal to stiffness matrix of the element 1 multiplied by the global displacements. I can do the same thing for the element 2. It is the same. Now I have 2 forces associated with the element 2. So that is F1 and F2. These are the elemental nodal values, and these are the members of element 2, okay, multiplied by the stiffness matrix multiplied by the global nodal displacements. I will extend it again. So remember that F2, so node 2 of element 2 is the node 1 in the global system, and first node of the element 2 is the node 2 of the global system. As a result, forces will be the first and second element of the global system. Then I have the stiffness matrix, which is written according to the global system, and then this will be multiplied by the nodal values in the global system. Therefore, I will obtain this expression again. A vector with a 3 component, a 3 by 3 matrix is equal to 3 by 3 matrix multiplied by a displacement with 3 components, or vector with 3 components. Okay, if I substitute these expressions into the force equilibrium, now I have this, because these are the forces, right? These two expressions gives me the internal forces, and I have external forces which I know, and I have reaction forces. As a result, global stiffness of a system is sum of the elemental stiffness matrices. You see? And I have this global stiffness matrix. Look at the elements of it and look at the structure of this global stiffness matrix. So remember that the element stiffness matrix was symmetric, and also the global system, the global stiffness matrix is symmetric as well. Okay. So this is one approach in obtaining the global stiffness matrix and the relationship between the nodal forces in the global system and nodal displacements. Now we form the global set of equations. There is another way of obtaining this system. We will see it in the next video.